morning, everybody. Welcome to this ADAS Applications with VI Grade Solutions webinar. I'm glad to host this session of the webinar. My name is Francesco Ambrogi, and I work as Consulting Services Manager for VI Grade. And today I will be supporting this webinar together with my colleague Mark Westaway, who is a driving simulator expert. In today's session, we are going to talk after a brief introduction about how different ADAS systems can be integrated and simulated within the VI grade environment. We will show some application, including the usage of a driving simulator, and there will be a session at the end for giving question and answers. So I would like to invite you to use the chat in the WebEx application to type your questions. We will collect them and then we will try to answer at the end of the presentation. Also, I would recommend everybody going on mute in a way that background noise is not disturbing the presentation. So just to briefly introduce the topic that we are going to cover today, we can rely on some of the most relevant trends that are related to the nowadays automotive market. This information is coming from Goldman Sachs, and basically what we can see is that from now up to 2025, some trends will be showing up very importantly in the automotive market. So we are going to have automobiles that will be more and more connected, supporting autonomous driving, eventually shared in the usage, especially in the Western countries, and there will be a trend through electrification. So all these trends are setting up important challenges to the process that is related to the creation and implementation of new vehicles. And this is making appearance with regard the automotive technology from different points of view. First of all, from the market, we're going to have less time and budget available, so the cycle to develop a new vehicle will become more and more shortened. At the same time, the product will show an increase in complexity due to the different systems that are going to be integrated into the vehicle. And also from the process of developing a new vehicle, there will be additional challenges related to the fact that more validation will be needed. So for this reason, the traditional development process appears to be not completely tailored for the new challenges. So in the old style vehicle development, we were supposed to go from a concept to a sign-off phase of the vehicle, going through different phases which are from time to time seeing the appearance and the usage of hardware testing, which is on the other side showing up at a late phase of the development process. So this could be an issue because of the new challenges that are set from the modern subsystems. So for what regards the ADAS, the process of integrating the ADAS system requires an integrated development approach. So the fact that the process of creating a concept and only in a later phase the availability of prototypes is making this process too slow. It is also could be also difficult to apply this process because simply the ADAS systems are requiring a lot of miles to be driven to certify the prototypes, and this is posing an additional problem. And of course, all these aspects listed before are also showing an effect on the costs, and so the cycle, as it was tailored before, is to be very expensive. So as VIA Grade, we are trying to set up a set of solutions that could help to make this process smarter, basically bridging the gap between testing and simulation. And this is realized mainly by introducing a virtual environment in which it is possible to analyze and test in an early phase of the development process the vehicle. So the usage of the driving simulator could be the bridge in which the development process can benefit the advantages of being faster and at the same time accurate. So as a result, we could transform the weakness that are characterizing the traditional development process into strength points. So it would be quicker, easier, and more affordable to implement and develop a new vehicle. In order to do that, we rely on an open environment that, as I said, is consisting in different components, the main one being the driving simulator, and which could be integrating different type of technologies. So we can mention the multi-body as a typical CAE approach to vehicle development from the point of view of the engineering, but we can also include in the same environment other tools that are more focused on development of systems and controllers, up to the point in which we can interact at the early stage of the development process with prototype and hardware components within the environment. Finally, the driving simulator, we can have also the human being part of the process and being able to test the vehicle performance and vehicle characteristics right from the beginning of the development process. So if we focus on the specific application related to implementing a driver assistance system, we can face it from different point of view. So we can start from offline and compare to what is required to test the same system in the real world. If we talk about the pure virtual simulation, so what we call the offline approach, there are some components in the environment that would be required. First of all, we need a vehicle model that is representing the properties of the vehicle and the dynamic response of the vehicle. We can eventually populate this model, including controllers that are now part of the vehicle environment. Besides to that, we must think about a proper scenario in which this vehicle model should be exercised. So we need a simulation environment in terms of traffic and in general of environment in which the model can be simulated. we need a driver model, and also we need to set up a set of events in which virtual sensor model can be tested. So if we look at the same type of application, same type of study in the real world, the approach is very similar, but the difference is that in this case we will have a full set of prototypes being in the game. So the vehicle would be a real prototype, the controllers would be hardware in general, the scenario needs to be set up in a proper environment to be safely tested, and of course we will have the presence of a real driver with sensors and event that we want to create and simulate to assess the different functionalities that we want to study. So we can understand that, especially in terms of events, setting up the specific condition in which you wanted to test a given ADAS function may pose some remarkable challenge. So if we combine now the two things together, we may have an environment in which all these things can be used at the same time, taking advantage of their availability at the different stages of the development process. So in this case, for example, if we consider the driving simulator as an integration platform, in this environment you can have the virtual vehicle model, virtual controllers, but could also integrate with hardware controllers the scenario that you want to test. And at the same time you can implement real hardware sensors that are excited by the input coming from the visuals, for example, or from the radar, that are part of the virtual environment. And in all this scenario, the human is also playing a role. So you can get the feedback that the driver could provide using a real prototype directly on a driving simulator. So here we can see a couple of movies in which we show this application on our driving simulator. For example, here you see our driving motion driving simulator, dynamic simulator, in the scanner environment, in which we can provide the specific traffic condition and also specific scenarios, so country, highway, or consider the effect of the weather during the simulation. In this context, it is also possible to interact with specific additional entities like other vehicles, pedestrians, animals, and whatever you get in touch during a real testing session, including the possibility of having a virtual representation of an ADAS system and sensors. Specifically with regard to the sensors definition, we could also do a further step in order to test the real sensor or virtual sensor in this environment. So, for example, in this video you see an application related to again a driving simulator, in which beside the typical components like active seats and belts that are provided with our simulators, of course the vehicle model, it is possible to test specific functions that are part of ADAS systems. So, for example, we could implement an autonomous driver that could be directly tested. So here you see that the driver is activated, and basically the automatic control algorithm is taking control of the vehicle, and it is possible to manage also the transition between the machine and the human. or it is possible to focus and reproduce highly dynamic maneuvers, comparing the automatic behavior of the autonomous driver with the purely human behavior, or also combining the two in the assisted configuration. So this is basically to give you an overview about which are possible applications that are available when using a driving simulator, together with the proper modeling of ADAS systems and sensors. So now I would like to hand over to my colleague Mark, in order to have a deeper insight about some of the applications that we have been implementing.
Yeah, thank you, Francesco. Yeah, so just to go into a little more detail of the things that's already been described in the presentation so far. Here we can see the general architecture for using VI Drive Sim for ADAS applications. And the way this is working essentially is that Drive Sim is acting as the hub. So everything is coming through Drive Sim, which is the real-time system, which is of course entirely necessary if you're doing driver human in the loop test cases. And you can connect, of course, you have the hardware side of things. So in this case, you could have a radar or a camera, and these are connected to the Drive Sim ecosystem and are communicating in both directions. So we can send information to a camera and then receive the information back. On the same side, on software, you can plug in traffic environments, sensor models, and so on. And the big benefit of this solution is these extra components are entirely exchangeable, so you're not forced to use specific hardware or softwares. So to give you an example of some of the test cases we've built up at our sim center using the DIM, we wanted to introduce a lane detection system. So we ended up setting up the environment as you can see here now. So in this case, we have a physical camera, which was pointed at a screen, looking at the image generated from the virtual environment. The camera then is also connected to an ECU, in this case, the NVIDIA Drive PX2, and it's receiving the image from the camera, and the onboard AI is processing this image and it's searching for the lane markings. And the lane marking information is then output from the ECU, fed back into the Drive Sim ecosystem once more, at which point it can then be picked up by the ADAS controllers and used to control the vehicle in some way. Going a little bit further into this test case, there are some additional possibilities. So as I said before, we had the camera pointing at a screen, so the projected image on a screen or on a monitor. Alternatively, you can inject the image directly into the NVIDIA board in this case, so you can bypass the need to actually point the camera at a screen. And a nice option in this case is, because we had the ground truth for the lane markings, we could compare the output of the lane net, the AI, which was calculating the lane markings, with our ground truth reference, and then you can of course tune the system and validate that it's working as you would expect. Another test case we set up was using a radar instead. So in this case, we had this radar target simulator. So we again put it into connected it to the Drive Sim ecosystem as shown in the previous slides, and more or less the same concept applies. So in this case, actually, we would use the virtual sensor inside the traffic software to detect the object, the virtual object that is. We then send this virtual object position and information to the radar target simulator, which then will stimulate a physical radar, so the radar that you would end up using on the actual car in reality. So you stimulates this radar, and the true output, let's say the real output that you would expect to find on the real car, is then fed back again to the drive sim ecosystem and can then be picked up by any ADAS controllers that you have present. And these can either be software in the loop or they can be additional hardware. And of course, there's the ADAS controllers can then influence the dynamics of the vehicle. On top of this, it's clear that for full ADAS applications, you need to be able to run multiple sensors in parallel. So the VIO Drive Sim solution is capable of supporting this. So we set up a test case with Conrad Technologies, running the camera and the radar simulator in parallel, all running in real time. And the concept is exactly the same as I described before, where we are generating virtual information, virtual data of the simulated objects, sending them to the real simulators, the radar and the camera in this case, which are stimulating real components. And then the output of these real components are going back to the real-time system, which can then be used by ADAS controllers to control the vehicle. So we have shown how to set up, or the possibilities with setting up the hardware and the simulator side of things. Of course, you also need an environment to actually test the systems to check if they are working as you think they are. So we've built this driver assistance experience, and it's essentially just a big world with over 100 kilometers of drivable roads with different conditions, different types of roads. So you can see we have highway, back roads like countryside, mountains, also urban environments. There's more than 50 actors and various types of actors, so not just cars. There are pedestrians, motorbikes, cyclists, and so on. And additionally, it's possible to adjust the weather, and this is possible also during runtime. So you can have dynamic weather conditions, so changing from a nice sunny day to stormy conditions as you please. On top of this experience, we built some controllers, so you can experience the effect these controllers might have, and how this might influence the human perception side of things. So in this case, we have the emergency brake, and we have set up some predetermined situation. So you would drive around in the urban environment. There will be various cars and so on driving around randomly, but at the same time, we've set up some triggered events. So if you want a repeatable case, in this case, we have set up an area where the pedestrians are waiting for you to drive by, and they'll run out in front of you. So this is nice because you can then repeat the situation over and over again and understand if there are some flaws in the AEB system. Another system we've implemented is the ACC, so the Adaptive Cruise Control. Again, in all of these graphics, you can see in the bottom left, there is the Conrad radar target simulator. So this is receiving the virtual object data and then simulating it to be received then by the physical radar, and it's fed back to the real-time system. And on the right side at the bottom, we can see all of the different feedback that is coming to the driver. So on the dashboard, you have the visual cluster, and of course the ACC in this case is adapting the longitudinal speed of the car, so you do not follow too closely to the vehicle in front of you. Then we have the lane departure warnings. So again, the same environment on the highway, and in this case, it's providing the driver with a warning when the driver is too close to the edge of the lane markings, and this is provided to the driver visually on the dashboard, as you can see in the bottom right. display. But also there's possibility to add vibration to the steering wheel, so it's a clear indication to the driver that they should pay attention and move back to the center of the lane. Then the obvious next step after lane departure warning is the lane keeping assist system. So you can see again, we're still using all of the same bits and pieces, so no need to completely rebuild everything from scratch. And this system is essentially using the same idea as the lane departure. So there's the camera detecting where the lane markings are, or alternatively using the ground truth. And it's providing a steering input to return the car back to the center of the lane once a certain threshold has been reached. On top of this, there's also acoustic feedback to the driver, so an auditory alert saying, I'm going to take over and move you back into the center of the lane. And the final system we've built as all of these as for demo purposes is the autopilot, which is essentially a combination of the adaptive cruise control and the lane keeping, but instead of the lane keeping only being active when you are moving to the edge of the road, it's active all the time. So the driver will stay in the center of the lane, will navigate the corners in the road as appropriate. So we talked about how everything is implemented, but now I want to talk a little bit about the options you have. So what products are available to the customer, and we would start with the desktop simulator. So this is very much the entry-level solution, and the intention of this simulator is for initial testing, preliminary steering feel, model stability validation, and so on. But you are quite limited in the human immersion in this case. So the next step up is the compact, and this adds quite a bit more for the human side of the validation and evaluation of the ADAS system. So you have a much larger screen, high quality image, you have a high quality steering system, so you can get some good and meaningful steering feedback. And this system can also be kitted out with the active seat and active belt technology that is available. And these will actually provide contact forces to the human. So you can actually start to evaluate whether the dynamics, so how the car is reacting to the ADAS controller's inputs, whether it's too strong or too weak, and so on. You can start to do this on this type of simulator. However, there's still quite a lot of immersion that can be added to the system. So in this case, we have the static simulator, and this is essentially the simulator that's ready. You want to start doing true evaluation of human in the loop driving with ADAS and HMI studies in mind, because in that case you need the driver to be very much in the environment. Again, the active seat and active belt technology is available on this system, providing contact forces to the driver. And additionally, on top of that, there is the shaker system to provide vibrations through the chassis. And finally, we have the full dynamic solution, which is essentially taking your static cockpit and putting it onto the motion platform, which is a 9° of freedom motion platform. And this, of course, allows you to actually give some inertial feedback to the driver, to the inertial forces. And this, again, adds an extra layer and level of feedback and immersion to the driver. So you can capture even more the quality of the controllers you're testing from the driver perception point of view. Moving it on to a little bit more detail of the DIM. So for the DIM 250, it would look something like this. So you have the motion platform, as I just described, the 9° of freedom. This is all floating on top of the base frame, so it's on magnetic air pads for minimizing the friction between the two surfaces, so it's moving around seamlessly. You have your cockpit on top, which you can use alternatively as a static. And you have the big conical screen and the high quality projectors to really truly immerse the driver in the environment you are testing. On top of this, there are various hardware accessories to choose from. You can define exactly the steering assembly you want, what configuration that you would like it. You have the active seats and belts, rear and side mirrors. Of course, they are important, especially for ADAS applications where you actually will be looking behind you on highway scenarios and so on to see the other cars around you. There is then the active brake. So this system is so you can tune the feeling of the brake pedal, how hard, how soft it is, the progressiveness. Additionally, any feedback coming back through the pedal, such as ABS. Then we also have the biotelemetry and eye tracking systems. And this is to add some objective results to the human driving. So it's very nice having subjective feedback and subjective data. But it's also nice to have objective, some numbers to look at sometimes. So this allows you to objectively analyze the human's reactions to specific events. And finally, we also have the shakers and speakers to, again, completely immerse the driver in the environment. And finally, you can add all sorts of sensors and hardware in the loop, such as cameras and radars and so on. So let's say in summary, we've shown how VI Grade is approaching the ADAS environment and the task at hand and the problems to solve. We've seen how the traffic and sensor elements can be included into the modeling environment, connecting reality and simulation. And finally, some clear examples of this technology used in practice. So I'll now pass you back to Francesco, and if we have some questions, we can go ahead and answer them.